Small block of mass 0.15 kilograms is placed at point A on this track at a height 2 meters above the bottom of the track. Released from rest, slides with negligible friction down the track around the loop, radius 0.6 meters, and leaves the track at point C, which is 0.5 meters above the bottom of the track. In part A, we want to calculate the speed of the block when it leaves the track at part C. So because this is a curved track with no friction, we're going to use conservation of energy. This up here will be the initial position. This over here will be the final position. So just set up Ki plus Ui equals Kf plus Uf. Initially, it has no kinetic energy since it's released from rest. It does have gravitational energy because it has height. It has final kinetic energy at this point because that's the speed you're trying to solve for. And it also has final gravitational energy because it's that certain height above the bottom of the track. So use this, plug in the formulas, solve for V, you'll get about 5.5-ish meters per second. Part B, on the dot, we want to draw the free body diagram when it's at the top of the loop, right there. So at that point, it has a gravitational force going straight down, and the surface is above it, so the normal force is also going straight down, and that's it as far as the forces go. If you want, you can label the fact that there is going to be a centripetal acceleration also going down because it's pointing toward the center of the circle. In part C, calculate the minimum speed the block can have at that highest point, at point B, without losing contact with the track. So you know what happens in that case is we set up Newton's second law for circular motion. That is, remember, this is Newton's second law for circular motion, not for rotational motion. There's a difference. The second law for rotational motion, just as a side note, I'll put it up here, is that one we just did recently, net torque equals I alpha. We're not using that here. We're using Newton's second law for circular motion. That should be a y. Net force in the y direction equals mass times centripetal acceleration. So if we make downward the positive direction, we have Fn plus Fg is equal to mac. The minimum possible speed will be where it just barely starts to lose contact with the track. So in other words, the Fn goes to 0. Plug in some formulas. Mg is equal to mv squared over r. Cancel out the m's, solve for the v, and you'll get about 2.45 meters per second. And then in part D, so if that's the speed you need right here, 2.45 meters per second, what is the minimum possible height you could release the block from? It's already been established that by releasing it from 2 meters height, it'll make it all the way through the loop and over to the other side of the track. So there's a certain height, a little bit less than 2 meters, where it'll just barely make it through the loop. So we can find that using conservation of energy. This time, the initial part will still be the same, but the final part, instead of being here, will now be at the top of the loop. So Ki plus Ui equals Kf plus Uf. Initially, it was released from rest. It does have initial gravitational energy since it's got height again. It has kinetic energy because it's moving at that point with a speed that we just calculated. And it does have gravitational energy because it is a height above the ground. It is double the radius, so it's got a height of 1.2 meters. A lot of people tend to forget that, that term. So for the h, the initial h, and the initial h, you get a height of 1.5 meters. So as long as the block is released from 1.5 meters height, when it gets to the top of the loop, it'll have a speed of, we said back in part C, of 2.45-ish meters per second, which is just enough to make it through the loop without losing contact. Alright, in part E, let's suppose that we're doing this with a sphere, and so if we use a sphere that rolls without slipping instead of the block, in part E, would the minimum speed needed at point B, the top of the loop, be greater than, less than, or the same as it was for the block? And what we used to find the block was V is equal to the square root of R times G. If you went through this back here, cancel out the M's and rearrange it for V, that's the formula you would get. And you can see that only depends on the radius of the circle and on G. So even though it says justify your answer without calculations, it's okay to justify it with just by putting an equation down and explaining what's in the equation, as long as you're not actually going through and like plugging numbers in the equation and solving it. So this is acceptable to give this equation and then talk about the fact that the speed of the sphere would have to be the same as the speed of the block, since it doesn't depend on anything other than the radius of the loop and the acceleration of gravity. Now in part F, so since it needs the same speed at the top of the loop, in part F, does it need to be released from the same height, or would it have to be released from a little higher or a little bit lower? And the way conservation of energy works for a rolling object is that when the object rolls down this ramp and through the loop up to this point, when it's right here, it has that speed, that necessary speed of 2.45, but it's also going to have a rotational speed, which gives it a rotational kinetic energy. So in order for energy to be conserved, to give it that same speed plus the rotational speed, it would actually need to be released from slightly higher. So that higher gravitational energy of the, I think we calculated it as 1.5 meters. So it would have to be released from a height a little bit above 1.5 meters, so that when it gets to that top point, it has both that necessary 2.45 meters per second plus whatever the rotational part of it is. In part G, the rotational inertia of a solid sphere is given by 2/5 mr squared. So determine if the sphere, if we release it from this same 2 meter height as the block, would ever lose contact with the track. You've got a couple different options for this one. I'll give you the two most obvious, and I'll let you pick which one you want to do. You can set up conservation of energy the exact same way we did in part D, the only difference being that you now have to add in that rotational part, the 1/2 I omega squared, where I is equal to 2/5 mr squared. And from that, you could calculate the initial height needed to put the sphere. We found the initial height needed for the block was 1.5 meters. If you calculate the initial height necessary for the sphere, you find it is 1.62 meters after going through the calculations. So since it's released from 2 meters height, then that is a sufficient speed. Another way you could do this, which is probably the more obvious way, is to go ahead and assume it's released from 2 meters height, and then just calculate what is the speed of the sphere at that highest point. Keeping in mind it has the rotational part also, and if that speed is greater than the 2.5 meters per second determined in part C, then it'll make it through without losing contact with the track. And finally, part H, is it realistically possible that the block could slide without friction and the sphere could roll without slipping on the exact same track, or would you need two different tracks with the same dimensions? Well, this is actually probably a more obvious question than most people are realizing, because for the block to go down the track has to be completely frictionless. But if the sphere goes down a completely frictionless track, then it's just going to slide. It's not going to roll. You need the friction to help a rolling object move along. It's kind of like when you go to a bowling alley. If you bowl really fast, because the bowling lane is so slick, you'll see the ball sliding, and sometimes you can get the ball to slide the whole way down without actually rolling at all. So same kind of idea for this, that you need friction on the track in order to get the sphere rolling. So you would have to have two different tracks with the exact same dimensions, one with friction and one without friction.